Let us continue our study of sequences with proposition 6, 1, 12 next. Convergent sequences are Cauchy. That's just what the proposition is. Suppose that the title says it all. This is a convergent sequence of real numbers. Then this is also a Cauchy sequence. And we will see the proof in one of the exercises. In the fifth exercise, we will prove this. There is an example illustrating this fact. The sequence this alternating sequence whose terms alternate between -1 and 1. Etc. is not convergent. Oh, sorry, it's not Cauchy sequence. Is not a Cauchy sequence. The reason is this. The sequence is not eventually one close. For Cauchiness, the sequence has to be eventually epsilon. Oh, sorry. It's not close, one steady. I confused myself between closeness and steadiness. For the sequence to be Cauchy, it has to be eventually epsilon steady for every positive real number epsilon. But this sequence is not eventually one steady. No matter how far down the sequence you go, no matter how many terms you remove from the beginning of the sequence, you cannot make all the terms, the difference between any two terms after that stage, after that initial removal, all of them less than or equal to 1. So that's why it is not eventually one steady. And the reason is simply that even after removing as many terms as you want, finitely of course, from this sequence, from the beginning say, you will still have the terms, the numbers 1 and minus 1, and the numerical difference between 1 and minus 1 is 2, and 2 is not less than or equal to 1. So because of this inequality, the sequence fails to be eventually one steady. So that's why since it fails for this particular value of epsilon, if you take epsilon equal to 1, it is not eventually epsilon steady for that value of epsilon. So it is not a Cauchy sequence. Now according to this proposition, every convergent sequence has to be a Cauchy sequence. So since this is not a Cauchy sequence, so consequently it cannot be convergent also. That is what this example says. And hence is not a convergent sequence by this proposition. So that way one can use this proposition. Now remark, for a converse to this proposition, for a converse to proposition 6, 1, 12, we have to go to the section 6.4, C, which of course we will see when the time comes. Theorem 6.4, 18. Okay. Now we show that formal limits can be superseded by actual limits. Just like formal differences means subtraction actually. Yeah, in fact the author uses subtraction, this word. Formal subtraction was superseded by actual subtraction let me refill, running out of ink. when we constructed the integers and formal division was superseded by actual division when we constructed the rational numbers. And it's given by this next proposition. And naturally its name is just this: formal limits are genuine limits. And the statement is this: suppose that an, where n varies from 1 to infinity, is a Cauchy sequence of rational numbers. Then an converges to the formal limit of the sequence. That is, the formal limit is equal to the actual limit. The proof of this also we will see in one of the exercises. Specifically in the 6th exercise. So once we do this, then our construction of the real number system from the rational number system will be complete. Once we prove that formal limits are nothing but actual limits in this sense. Okay, now next we define something which we have, a notion which we have already come across for sequences of rational numbers, namely boundedness of a sequence. We are now going to do it for sequences of real numbers. Definition 16, bounded sequences. Oh, and one more thing is that you may be noticing that here the index n starts with 1, but these things are not important in our study of sequences. Where the sequence starts actually does not it does not affect the situation, because we really are studying what happens to the sequence eventually. What is its overall, I should not say overall, but what is its limiting behavior? What the tail end of the sequence does when we remove finitely many terms from the beginning. That's what we are after. So where the index starts, it starts at 1 or some other integer. That actually does not matter. So instead of writing the index here varying from 1 to infinity, you can also take a general integer m. Nothing much will change, only the proof has to be written slightly differently than the ones that we will write in the solution to this exercise. Anyway, so we now come to bounded sequences. Suppose that a sequence, this is the definition, a sequence an where now n varies from m to infinity. That's why I thought of saying something about this. A sequence is a sequence of real numbers. Although we are dealing with real sequences, but we should formally, when we are defining something or stating a result, we should be specific about the things that we are using. A sequence of real numbers is said to be bounded by the real number m if the absolute value of all the terms of the sequence are less than or equal to m. Okay, so that is the definition of being bounded by a positive real number. These conditions tell us that m has to be positive. If we take m to be negative, then it will not make sense, because absolute value of any real number is a non-negative real number itself. We say that an is bounded. Simply, we say that it is bounded if it is bounded by some positive real number m. And m in this context is also called a bound for the sequence. So because this definition is just like the one given for a sequence of rational numbers, so we write after this definition is consistent . with definition 5.1.12. And the consistency has been investigated in exercise 6.1.7. So there we will see what the deal is with this thing. Recall that lemma 5.1.15 states that every Cauchy sequence of rational numbers is bounded. We have already seen this in lemma, that is the statement of lemma 5.1.15, and we have proved also that every Cauchy sequence of rational numbers is bounded. Now in the proof of this result, this lemma, if one looks at the proof carefully, if one studies the proof, one will notice that real numbers can be replaced with, rational numbers can be replaced with real numbers, and still the proof works, the proof goes through. So the same can be stated also for real numbers, that is, every Cauchy sequence of real numbers is bounded. Now that we have a definition of bounded sequences of real numbers, we can now state that. So the author writes an inspection of the proof of this lemma reveals that the same arguments work for real numbers. That is, every Cauchy sequence of real numbers is bounded. That's what we get. In particular, from proposition 6.1.12, we get this corollary. If we combine all the results in the right way, then we get this corollary. Every convergent sequence of real numbers is bounded, because proposition 6.12 tells us that if we have a convergent sequence of real numbers, then it is a Cauchy sequence. And right now we have said that this lemma, it can be generalized from sequences of rational numbers to sequences of real numbers. That is, any Cauchy sequence of real numbers is bounded. So convergence of a sequence of real numbers implies its Cauchiness by this proposition, and Cauchiness then implies boundedness. So that's why we have this corollary: every convergent sequence of real numbers is bounded. And this fact can be used to rule out some sequences from the class of convergent sequences of real numbers. In the next example, we see that. The sequence that is the sequence of positive integers is not bounded, which we already know, and it's very easy to show also why it is not bounded. So since it's not bounded, by this corollary it cannot be convergent also. This is convenient, because you see, if you just simply want to use the definition of convergence of a sequence of real numbers to show that a real number a sequence of real numbers is not convergent, means you have to show that the sequence does not converge to any real number. And it's not obvious how one can approach such a problem if one just has to use the definition of convergence. However, this necessary condition that convergent sequences must be bounded can be used in some such cases in a very successful way. You don't have to think about showing that the terms are not approaching anything. You don't have to think in those terms. You just need to observe that this sequence is not bounded. So that's why this necessary condition for convergence has been violated. So the sequence cannot be convergent. And hence, by corollary 6.117, it cannot be convergent. Okay. And finally, let us now state the limit laws. We will prove the limit laws, of course, in the exercises. We can now prove the usual limit laws, and it appears as theorem 19. let an and bn be two sequences of real numbers, and let x comma y be the real numbers. Is it enough to just say sequences? We took convergent sequences because then only their limits will exist. So x is the limit of the first sequence and y is the limit of the second sequence. Okay. Now come the parts of this theorem. Part A. The sequence an plus bn converges to x plus y. In other words, limit of an plus bn is limit of an plus limit of bn. Okay. The limit of the sum of two convergent sequences is equal to the sum of their limits. In part B, the sequence, now after sum we have product. an bn converges to xy. In other words, limit of an bn is this times this. The limit of the product of two convergent sequences equals the product of their limits. Then in part C, multiplying a sequence by a constant for any real number, C the sequence CAN converges to CX. In other words, we have this. Then in part D we have difference, I think. Yes, in part D we have difference. The sequence an minus bn converges to x minus y. In other words, limit of an minus bn equals limit of an minus limit of bn. Keep in mind that these results are true only when both the sequences are convergent. If only one of them is convergent and the other is not, then these things will not make sense. I mean, these results, these final equations. Then part E. Suppose that y is not equal to 0, that is the limit of bn is not equal to 0, and also that all the bn's are also non-zero for all n greater than or equal to m. Then the sequence bn in bn inverse means we should not say inverse, but bn to the power minus 1 over bn, reciprocal of bn. That sequence converges to x inverse. In other words, limit of this is not x, no, it's y. Y is non-zero. Limit of bn inverse is equal to limit of bn, I mean to the power minus 1 is this. Like that, we have part F, where we also involve the sequence xn. The beginning is same, the initial hypothesis. Suppose that y is non-zero and that bn is non-zero for all n greater than or equal to m. Then the sequence an divided by bn converges to x divided by y. In other words, limit of an divided by bn as n approaches infinity is equal to limit of an divided by limit of bn. And then there are two more parts, G and H, which involve maximum and minimum. The sequence whose nth term is the maximum of an and bn converges to the maximum of the two limits. In other words, limit of the maximum is equal to the maximum of the limits. Just like that, there is a minimum one also. This converges to minimum of x comma y. In other words, limit of the minimum is equal to the minimum of the limits. So these are all the quite a few subdivisions of the 19th result, which is the last result of this section, and its proof, just like the others, has been moved to the exercises. So here this section ends. After this, let us now look at the exercises, a few of them. So the first one is this. Let an be a sequence of real numbers such that the hypothesis an plus 1 is strictly greater than an for all natural numbers n. Prove that whenever m and n are natural numbers such that m is greater than n, then we have am greater than an. We have to prove this. We refer to these sequences, sequences which behave like this, as increasing sequences, because as we increase the index value, the terms also increase. Okay. For this, we are going to use a sort of induction argument, specifically this. We apply strong induction on this variable m minus n. There will be other ways of solving this, because two natural numbers are involved. One may choose to induct on one of them, keeping the other constant. However, let us just see this somewhat different approach also. This is also induction, but we are not inducting on m or n, but rather on m minus n. Now m minus n, according to the way this whole thing has been presented, is a positive integer. Okay, so that's why we are saying we are applying strong induction on this. Note that m minus n is a positive integer, since m is greater than n. Because what is it that we have to show? It is given that, say, m and n are natural numbers such that m is greater than n. We then have to prove that am is greater than an. So depending on what m and n are, m minus n will be determined, and so there will be many cases what I am trying to say here is this. Say m minus n, the smallest possible value, since m is greater than n, the smallest possible value of m minus n is 1, and that one can appear for different types of values of m and n. For example, you can take m equal to 2, n equal to 1, or m equal to 3, n equal to 2. So when we are applying induction on m minus n, all those infinitely many cases for m and n to give us 1 will be handled in only one step. Okay, so it makes the solution somewhat easier. So that's why we write when m minus n is equal to 1, that is the smallest possible value, then keep in mind that in this single case there are infinitely many choices for m and n. because after all they are just natural numbers differing by 1, where m is the larger one. Then the result means this one, that am has to be greater than an. Then the result is just what is given, the hypothesis, because you see in this case m is n plus 1, so am is greater than an. Just the hypothesis this. So this is the basis for our induction. Now assume that the result is true for all integers m minus n, such that k, where k is some positive integer. Here also, just like the basis case, just like the base case, there are actually infinitely many values of m and n that will give us in fact even just one value between 1 and k. Just like that, for the other values also there will be infinitely many pairs of natural numbers m and n whose differences are all equal to that number. So all of these things are part of this induction hypothesis. Okay. Then an plus k is greater than an, because the induction hypothesis means what? Am is greater than an. That is the induction hypothesis when m minus n is less than or equal to k. In particular, if m minus n is equal to k, then m is equal to n plus k. So for that particular case also this inequality is true, and this is that inequality. Okay. Since, but it's also given that if we add 1 to the index, then the term of the sequence increases. So since n plus k plus 1 is greater than n plus k, we have an plus k plus 1 is greater than an. That is, am is greater than an where m is, should we write it as m? Yeah, because m is a variable. Oh, but m is a variable here Here, however, the m I am going to use is this specific value. But is it really specific? Because I am going to write m equal to n plus k plus 1. N is changing. No, it's not specific. K is specific. K is some positive integer, but n can be anything. So that's why let us keep m as m. K plus 1, so that m minus n is k plus 1. So we are inducting on m minus n now. So now the result is also true if m and n are any two natural numbers such that their difference is k plus 1. Our induction hypothesis was about the cases where the difference is between 1 and k. So now if the difference is k plus 1 also, for such pairs also the inequality is true. And again I am saying this is not a single equation. This represents infinitely many equations where if you take some value of n, add a k plus 1 to that thing you take as m. You take another value of n, you get another value of m. So all those things are part of this equation. Okay. This completes the induction and proves the result. Okay, so there the solution ends. Then the second one, there are 10 exercises in this set of exercises. We will solve 5 of them in this video and the other 5 we will solve in the next one. Let an be a sequence of real numbers. Let C be a real number. C is some real number, and let m prime greater than or equal to m be an integer. Show that the original sequence converges to C if and only if the sequence where the index starts from m prime instead of starting from m also converges to C. This exercise tells us that if we remove a few finitely many terms from the beginning, then the convergence of the sequence or lack thereof is not affected. Okay, so the justification for that remark that we were making a little while ago, that is this exercise. So let's see the solution. First, assume that the original sequence converges to C, then for every real number, we are not mentioning that epsilon is real, okay, it's understood. Since real number system is the only system we have got so far, I mean, we have the other rationals, integers, natural numbers, those systems are also there, but the real number system is the largest one, which includes all the systems inside of it. So if we are not saying anything about a given symbol, you should understand that it's the most general one, it's a real number in the context of these studies. Okay, so then for every epsilon greater than 0, there exists an integer n greater than or equal to m such that this difference is less than or equal to epsilon for all n greater than or equal to capital N. Okay. In particular, we have for all n greater than or equal to n, okay, should I say it like this or should I add m prime to n? I think it will be better to add that. You see, convergence of the sequence to C implies that for every epsilon, we are writing the definition, we are using the definition of convergence here. For every positive real number epsilon, these inequalities are true for all indices n greater than or equal to capital N. In particular, if these inequalities are true starting from the stage capital N, then it's like this. These are the positive integers. Oh, I should not say positive. Okay. No, this way I cannot approach, because no one is saying that m is a positive integer. In particular, we have this for all n greater than or equal to n, such that n is also greater than or equal to m prime. Now here we have imposed one extra condition on the index n. These inequalities are already true for those values of small n which are greater than or equal to capital N. Fine. But we can impose something else also. No? We can impose, besides this restriction, we can also further restrict n to be greater than or equal to small m prime also. So if these inequalities are true for these types of values of n, then in particular among those values, those n which also satisfy these inequalities, for such n also these inequalities will be true. I mean, we are narrowing the range of small n further than what is allowed by this thing. In fact, what I am saying here is this: n is an integer and n is greater than or equal to capital N. This contains this as a subset. So because our inequalities are true for all n coming from this set, in particular they will also be true for all n coming from this subset. That's why we can write like this. But when we are restricting our index n to be greater than or equal to m prime, then we are talking about this sequence, which has been obtained from the original sequence by possibly removing some initial terms. I am saying possibly because it may happen that m prime is equal to m. In that case, these two sequences are identical. But if m prime is strictly greater than m, then those values that appear in the sequence where the index is smaller than m prime, they will not appear in this second sequence. Okay, so there we actually had to remove some things. Anyway, so now we are talking about this sequence and we are talking about its convergence. But there is one more small thing. You see, the definition of convergence demands that the stage from which our estimation starts, that is the stage from which these inequalities should be true, that stage should itself be starting after the start of the sequence itself, because otherwise it does not make sense. Now, if a sequence say starts from 10, A11, A12, etc., and you are saying that the terms of this sequence do something like this, they satisfy some inequalities starting from the index 5, say your capital N is 5. That does not make sense because A5 has no meaning. So that's why we need n to be greater than or equal to small m. Now here also, if we want to say from this last line that this sequence converges to C, we need a stage which is greater than or equal to small m prime, and we can achieve that like this. This original capital N may not be greater than or equal to m prime, that is not necessary. Thus, an minus c is less than or equal to epsilon for all n greater than or equal to maximum of n and m prime. Note that maximum of n and m prime is an integer this is greater than or equal to m prime, because if our n is greater than or equal to the maximum of n and m prime, then automatically it is greater than or equal to n as well as it's greater than or equal to m prime. So these two conditions are true, so the inequalities are true. Okay, and that's why we are able to write this statement. And now we can conclude. This implies this converges to C. So that is one half of the solution. Conversely, assume that this second sequence, the converse is actually easier than this one, converges to C. Then for any real number epsilon greater than 0, there exists an integer. Okay, since we can use epsilon, but for the sake of clarity or to reduce confusion, let us use epsilon prime. An integer n prime greater than or equal to, keep in mind, now we are in this sequence, so it has to be greater than or equal to m prime, such that this difference is less than or equal to epsilon. In this sense, it's all about the indices. So you see, we did not have to touch these inequalities at all. We did not have to do anything with them. They were just there simply because they are there. Okay, we did not have to change them or use them in any way other than just writing them. So this is less than or equal to epsilon for all n greater than or equal to n. Since m prime itself is greater than or equal to m, we see that this is less than or equal to epsilon for all n greater than or equal to epsilon prime, n greater than or equal to n prime, which itself is greater than or equal to m. Thus the original sequence also converges to C, and this completes the solution. Next, 3. Let an be a sequence of real numbers. Let C be a real number. Okay, so it's just like that previous exercise. It starts similarly, and let k greater than or equal to 0 be an integer. That is, k is a non-negative integer. Show that an, where n is varying from m to infinity, converges to C if and only if this other sequence an prime, an plus k, where again n is varying from m to infinity, converges to C. Okay, so this time we are not changing the starting points. I mean, at least apparently we are not changing the starting point, but we are changing the index itself from n to n plus k. The ultimate effect is that the starting point has changed, but the presentation is somewhat different. So naturally this solution will it can be obtained from the previous one. Writing m plus k equal to m prime, we note that m prime is greater than or equal to m. If we denote m plus k by the symbol m prime, then because k is a non-negative integer, so m prime will be greater than or equal to m. In fact, it will be equal to m if and only if k is 0. Keep in mind that k is a fixed non-negative integer. Okay, k is not changing, m is changing. Oh no, sorry, m is also not changing, n is changing. N is the variable. This and an plus k, where n varies from m to infinity, is equal to an, where n varies from m prime to infinity. Okay, this is a simple thing. When n is m, then the index here becomes n plus m. If n takes higher values, say m plus 1 or m plus 2, then the index of course will also be higher. I mean more than the smallest one. But here the things start at m plus k. Here also the things start at m plus k because m prime is m plus k. So that's why the two sequences are equal. They are actually two different ways of writing the same sequence. Now the result follows from the previous exercise. Because the previous exercise tells us that the original sequence converges to C if and only if this converges to C. So that's why if and only if this converges to C. Then exercise 4. What is it? Have I made a mistake somewhere? I mean, what was exercise 2? Oh, sorry, what the hell? Okay, what a mess up. Exercise 3 is this. So exercise, what have I done? The first the first exercise is okay. The second exercise is something that I have not solved here. Neither did I write the statement. The third exercise is okay. This was the third exercise. And this is the fourth exercise actually. Sorry about this. So since we have seen the third exercise and the fourth exercise, let us see the second one also. The second one actually is nothing very difficult. You remember the definition of convergence of a sequence was given in steps. That is, first we define epsilon closeness, then we define eventual epsilon closeness, and then we define convergence of a sequence of real numbers. So this exercise is about using those steps and writing the definition at once. Let me write it here. Let an, where n varies from 1 to infinity, be a sequence of real numbers, and let L be a real number. Okay, show that an converges to L if and only if and only if given any real positive epsilon. Real positive epsilon one can find Yes, one actually, strictly speaking, needs this exercise in order to use the definition of convergence directly without going into those eventual epsilon steadiness and all those things. One can find an n, you understand in this context n is an integer greater than or equal to m such that the usual things an minus l is less than or equal to epsilon for all n greater than or equal to l. Although it's easy to see why this is the case, but let's for once go through the details. We need to see this thing in detail for only once, and that will be done. I mean, then we can use the definition without going into those steps. First, assume that an is convergent to L. Choose a real number epsilon which is positive. Since this is okay, so then convergence means what? Having chosen one such epsilon, it means this sequence is eventually epsilon close to L. This is eventually epsilon close to L. So there exists an integer n greater than or equal to m such that this sequence is epsilon close to L. This means an minus L is less than or equal to epsilon. This sequence being epsilon close to L means that the difference will be less than or equal to epsilon for all the terms of the sequence. But the terms start from the index value capital N. So for all n greater than or equal to n. So if an is convergent to L, then this happens. Conversely, assume that for any real epsilon prime, to distinguish this from this other part, we are using the some other symbol epsilon prime greater than 0. There exists an integer n prime greater than or equal to m such that for all n greater than or equal to n prime. Okay. This means this sequence is epsilon close to L, but since n prime is greater than or equal to m, and for a given epsilon prime there is one such n prime, existence of such an n prime tells us that the original sequence is eventually epsilon prime close to L. Thus, the original sequence where the index starts from M is eventually epsilon prime close to L. But epsilon prime itself is any chosen positive real number. So, the original sequence is convergent to L. So, that is the solution. Now, finally, we come to exercise 615. This is the last one we will solve in this part in this video. Prove proposition 6112. Hint: use the triangle inequality. Or proposition 437, no need to go that far back, we will use the triangle inequality. But before that, let me refill. I think I am running out of ink again. Okay. So let us first recall what the proposition was. The proposition just says that every convergent sequence is a Cauchy sequence. Okay, so let I think in the proposition the statement is given, so we have to prove the statement. An is a convergent sequence of real numbers, but it's not given, the limit is not given, so that we have to assume. Let this converge to the real number, say L. We have to prove that the sequence is the Cauchy sequence. choose any real epsilon greater than 0, then convergence implies there exists an integer n greater than or equal to m such that this is less than or equal to epsilon by 2. Ideally we should write epsilon, but in place of epsilon we can write epsilon by 2 also. That is also a positive real number. For that choice of epsilon, for that choice of this number, this integer n exists for all n greater than or equal to n. Thus, for integers I and j, satisfying this, that is, now if I and j are integers both greater than or equal to n, we have this difference. This can be written as ai minus l plus l minus aj, and now we can use the triangle inequality of absolute value, or rather triangle inequality of distance, to write like this. This is less than or equal to this plus L minus aj. Now L minus aj, because we have absolute value, so we can use this for any real number x. Both x and minus x have the same absolute value. So here in place of L minus aj we can write aj minus L. Okay. Now since both I and j are greater than or equal to n, we can think of them in place of n, each one of them, and so these two quantities, both of them will be less than or equal to epsilon by 2, and they together give us epsilon. So what do we have? Let us write it in a compact form. We thus have this is less than or equal to epsilon for all integers I and j greater than or equal to n. So that is the condition for a sequence to be a Cauchy sequence. Hence this completes the proof of this proposition and also the solution. So every convergent sequence is Cauchy. The loose or casual way of thinking about this is that if the terms of the sequence get very close to something, some L, that is if it is convergent, then the distance between the terms themselves will keep on diminishing. The terms themselves will come close to one another. The converse to this thing is that if such behavior is seen in a sequence, that is if it is Cauchy, if the terms come closer and closer to one another as we go further and further down the sequence, then it should be convergent. And that thing is true in the system of real numbers, that thing is not true in the system of rational numbers, which is nothing but it's related to the least upper bound property. Okay, and that is why the real number line, the system of real numbers has been associated with the geometric object of a line which is unbounded on either direction. There is no gap or hole in the system of real numbers in this sense. So we will see the other exercises in the next video, and possibly along with that we will start the next section, the extended real numbers system, where to the real number system we adjoin these two symbols, plus infinity and minus infinity, and then we see how one can extend the ordinary order relation that we have in the system of real numbers to this slightly larger system. So those things we will see. So until then, until that happens, this is me, Lucifer, from a mathematical room. If you want to comment on these things, you can of course write in the comment section below, or you can mail me in this at this address. So that will be all for tonight. So see you in the next video. Have a nice night.